All right, now, color. So we have two blocks. Oh, by the way, guess what else? Everything you say is now being recorded. Hey.
Should.
All right, focus. I got two blocks, pulley, rope, spring, right? Free body diagrams is the first step. So for my 3.2 kilogram guy, I've got tension going up, force of gravity going down. For my 3.0 kilogram guy, I got tension going up, force of gravity going down, and force of the spring going down. Are we all okay there? The first step is always to get free bodies. If you get free bodies, it's not a big deal. I think that's starting to set in with y'all. Which way do you want me to pick positive and negative?
Top is positive.
Top, for which one?
The heavier one. No, the smaller one.
You want rotating this way. We're talking down, the 3.0 kilogram down to be positive?
No, do the other way.
Do the other way. Okay.
Look, you go.
You got it, Carol.
Finland.
All right, so there we go. We are going to have it rotating the 3.0 going down as positive, right? Please remember that you have to pick system positive, system negative. Otherwise, everything comes off. Next step, sum up the forces, right? So you look at your free bodies. You have your 3.2 guy, and all you care about is the y-axis because there is nothing in the x. Sum of the forces equals ma, and it's going to be tension minus Fg equals ma, right? And that's with me going up for the 3.2 is positive, down gravity. So I'm calling positive, rotating to where the 3.0 kilogram is going down.
If you did it the other way, would it be Fg minus T?
Yes.
Yeah.
Yes. All right, so there's that guy, and my 3.0. Once again, all I care about is the y-axis. There is nothing in the x, right? So sum of the forces equals ma. Now it's going to be opposite. Down is positive, right? So I have Fg plus, that's the force of gravity, plus Fs, that's the force of the spring, minus the tension, equals ma. You're welcome to, if you feel comfortable, go ahead and skip a step and start plugging in like Kx and Mg for Fg, things like that. But I gotta tell you, I recommend not doing that immediately, just so you get the habit of I look at your bodies and then I write it down. Okay? As you do this a lot, you'll get to the point where you're skipping steps. Don't do it too early though. You'll stunt your own growth of this. All right, if you try to jump ahead too much. All right, so it doesn't really matter where you want to start. I'll start with the 3.2 kilogram guy. Tension, I don't know that, so it's just T minus Fg breaks down into what? Mg, right? Mass times gravity equals Ma. I know what Mg is, right? So that's T minus 3.2 times 9.8 equals 3.2A. All right, I got a problem here, right? My problem is I have two variables. So I need to go to the other one. All right, so let's start plugging in here. Fg is going to be mg plus force of spring. Now, technically, it's negative kx. I'm going to talk about why it's negative kx here in a little bit. But right now, I'm telling you, drop the negative and deal with directions manually yourself, right? So just put kx in. That way you don't make it a negative force of spring. If you use negative kx, it's almost like you're subtracting it from the force of gravity, right? And we already know we should be adding it to the force of gravity, so don't worry about that negative for now. Kx minus t equals ma, right? So that'll be 3.0 times 9.8 plus 125 times 0.30, because it was in centimeters, 30 centimeters, so 0.30 minus t. Shift all this over so I get myself a little bit more room. Equals m 3.0 times a. Everybody tracking with me so far? Yep.
Yes.
I run into the exact same problem. I got a T and an A, but check it out. I got T and an A in the other. So you solve for T in one and you substitute into the other. That's system of equations, right? Let's just solve for A, right? So I'm going to, over here, realize that T is equal to 3.2A plus, what's 3.2 times 9.8? 3.2 times 9.8, please. 31.36. 31.36. So I took the 3.2 times 9.8 and moved it over to the other side. So I got a T equals, right? This allows me to plug that guy into this string. 3.0 times 9.8 is what? 29.4 plus 125 times 0.3. Sorry? 37.5 for 125 times 0.3. Let me pause. All I'm asking you is for you to take your calculator, type in 125. All right, 37.5. Minus, now here's where we're going to substitute in, right? I'm going to put in a parentheses to make sure I emphasize. I'm going to have to distribute this negative. 3.2A plus 31.6 equals my 3.0A. Okay. So now I can reduce a little bit more, right? 29.4 plus 37.5 is what? 0.966, right? Minus, now I got to distribute this negative, minus 3.2A minus 31.6 equals 3.0A. You all okay so far?
What is one number, right? 66.
Yes. Sorry that it all got spaced out. All right, so 66.9 minus 31.6. $66.9 minus 31.6 came out to be what?
31.6. That's the number.
I got too many people talking. Hannah. Oh, thank you. 31.36. All right, so now do that subtraction for me.
We're like, no, that's the answer.
35.54 minus 3.2A equals 3.0A. Next step, move that 3.2A to the other side. Right, so now I'm adding it over. So I got 35.54 equals 6.2A. Divide both sides by 6.2, so the acceleration must come out to be what? 1.73? 5.7.
Nice.
All right, 5.73 meters per second squared. Let's scroll back up. Let's check our sig figs. How many sig figs am I given in this problem? I got, with the dot here behind 30, I got 2, right? 2, 2, 3. So smallest one, I got 2, so this needs to become 5.7 meters per second squared is what your acceleration is. Okay. So if you come out with 5.8, that's fine, right? That's probably just a rounding thing in the calculators. You kept more sig figs than I did at some point, or I kept more sig figs than you did at some point. You know, you truncated, I rounded this. It's very minor stuff, right? So somewhere in there, maybe I took, maybe you didn't round your 3.0 times 9.8, right? and I ran to 29.4. I don't know if it came out to be exactly 29.4. I'm not sure, right? But it doesn't matter, right? That's small off, 0.1 off here. Think about percentages, right? 0.1 over 5.7, right? I mean, what percent are we talking about? Nothing, right? Next to nothing. Right? Your percent off is so small. We're fine. It's round. Okay. All right. Let me talk about springs. Why I'm saying you can drop the negative kx. Why it is kx. Now,
Where's my CDS?
I didn't what?
Find T.
Oh, yes. Let's go back to find T. Tension. All right. Now, tension should be pretty simple. Let's jump over here. Any of the equations work. Now, right, you have A. Any of them work. Take your A, plug back in. So I'll plug back into this one. T equals 3.2 times now my 5.73 plus 31.36. So T comes out to be
49.696.
49.6
Oh, I got
means with two sig figs, I got to round this up to 50 newtons.
Now, do we have two or just one for the 30 centimeters?
There was a decimal point behind 30. So you had two. Questions about the spell work? All right. Springs. Now, the reason it's negative kx is because whenever you're very careful with positives and negatives. Here I've got a spring and some mass M, right? Now, free body diagram of this is going to be force of spring going up, force of gravity going down, right? We're all cool with that. Do I see that? Now, if I tell you K equals 30 Newton meters, and I tell you this spring was stretched downwards, some displacement, 32 centimeters, and I want you to solve for M. Mass equals what? Okay. This is a problem that we've already done together. Sum of your forces. You only have one axis, the y-axis, right? So the y-axis, sum of the forces equals MA. I need to call positives and negatives. Which way do you want to be positive? Which way do you want to be negative? Down is positive. Gordon McKinley. So I got positive, and up here is my negative, right up top. So I've got FG minus Fs equals, what's the acceleration of the system? What's the acceleration of the system? 0, right? I mean, unless the thing's moving, which I just put it on there and let it stretch down, it's reached equilibrium, right? So the acceleration of the system is 0, so you get a 0 over there, right? This sets up your Fg equal to Fs, right? Which would mean mg equals Fs. Now, technically, the force of a spring is negative kx. Here's why I say don't worry about that. Let's start plugging things in. M is what I'm looking for. Gravity, 9.8 equals negative. My K, which was 30. And this problem I made it 30 here. Big problem. Now, X. Let's come back up and let's look at X. Now, technically, the spring force is going up negative, right? And the stretching goes down which way? The positive direction, right? So this would be, and I missed out something else here. But this is going to be a positive, what did I say, 35? 32. So 0.32 meters. Okay. Technically a positive thing, caring about that. Spring force is going up to the negative direction. But I already messed up here, right? You subtract it over. Let me check my negatives here. Right, so you come out with a mass that seems to be negative. Almost. I missed a negative somewhere, guys. I already know I missed a negative. Here's why I know it's negative somewhere. I'm not sure where. Force of a spring equals negative kx, right? But what can you tell me about the force and the displacement x? Force pulls which way? Like in this instance, force pulls up, displacement goes down. They go opposites of each other. That's why the negative sign is there, to counteract that. Okay, so force of this spring, if I told you force of this spring was 120 newtons, right? The force is going up, I call that positive, so the displacement must be negative 32 centimeters. That, in essence, is going to cancel out your negatives and give you your positive spring constant. The reason why there's the negative out in front is because force and displacement go opposite ways. Okay, that's the purpose behind that negative, to indicate the force goes the opposite way that you stretch the spring. Okay. Now, the reason I'm telling you don't worry about that negative too much when you're plugging into Newton's second law is because just guessing about you aren't going to be very good with figuring out, okay, now the force is going up in the negative direction, it's being stretched in the positive direction. That means I've got a positive displacement, a negative force, but I got to be careful not to cancel out my negatives like I've already done in that other problem, right? You don't want to negative your negatives. Okay? You know, end goal, your end result, is that, like in this problem here, your end goal is Fg minus force of spring. And you don't want another negative to enter this picture that is going to mess up this relationship that they're going opposite ways. Okay? That's why I say be okay dropping the negative there. Be okay dropping the negative there for the sake of practicality. Does that make sense to everyone? Okay, I mean, I even demoed this. I mean, I made some negative mistake in here already, right? I guess technically if I'm going to use your negative kx, I also need to use a negative 9.8, right? Maybe, or in there, some other negative somewhere. Okay? Don't worry about that. Let's get to the end goal. Let's be practical. That makes sense? I got a few head nods. Rest of you? All right. Now,
9.8 will you miss the negative one?
possible. I don't want to spend time going back and hunting, to be honest with you. Let's see, where were we?
I always do that use 9.8.
Yes. Do. Don't. Not math equals MA problems. Because if you use negative 9.8, you're more than likely at some point in time going to negative the negative. Right? Deal with directions manually with your forces out front. So use positive 9.8. And if the force of gravity is going down, you're calling down negative, it always goes down. And you make it negative mg, right? The negative is being taken care of. The direction is being taken care of. Right? Same thing with springs, right? Technically it's negative kx, but if you have already indicated the direction of the force, don't let that negative come and mess up your directions. Please don't. Okay? Just be very, very careful of what you're doing in there. All right? Don't let your directions get messed up. I guess we need to talk about your homework. Great. Okay. Acceleration of cart down ramps. It's only in 5 minutes. I'll do the demo later. I just want to talk about this. Now, whenever something's on a ramp, the ground goes up with some angle. Let's say this is 30 degrees here. Okay? And here's my object. Okay? Looks a little bit steep at 30 degrees, but oh well. Now, if I'm going to label all my forces on this as if it was the free body diagram, just to try to get an idea. So, which way does gravity go?
Down.
Straight down. FG. Which way does normal force go? Diagonal up, perpendicular. Yes, the surface. Normal force goes up perpendicular to the surface at all times. Now, if you have friction, if this object's going down the ramp, which way would friction go? Up the ramp, yeah, up the ramp like this, okay? If you had something down here at the bottom, let's say a string, and it was pulling it down, which way would that force go?
Parallel.
Down the ramp. So if you were pulling on it down the ramp, it'd go like this. Now, let me make this point to you. Notice how 3 of those vectors are all at 90 degrees of each other, and there's only one outlier, the force of gravity, right? So you have a choice now. You could either, whenever you have to break these guys into components, you could either use a traditional XY axis, okay? Use a traditional XY axis and break force of pull, normal force, and force of friction into components. Or we could tilt our axis and only have to break the force of gravity into components. Much easier that way. So instead of using a traditional one, we're going to use one that looks like this, where here's your y-axis and here's your x-axis. Y-axis is going to go down the slope. Did I get my angles relatively the same? Relatively. Y-axis is going to go down the slope. X-axis is going to be perpendicular. Let me try to translate that onto our object. Y, X. I know it feels like they're switched. They're not switched here. Instead, take a regular XY axis, okay? Take a regular XY axis, and instead of tilting the x-axis up a little bit, lay the y-axis down. Okay, instead of tilting the x-axis up, lay the y-axis down onto it. All right, and the reason why is going to become very aware right now here in a second. So I've got to figure out angles here, right? I've got to figure out an angle here so that I can divide this force of gravity into components. Do I see that?
30 degrees.
So it's going to be 30 degrees that we're going to use, right? What can you say? Let me extend this guy down. What can you say that angle is? 60, right? This angle must be 60 because I got a triangle there, right? Total of all the angles must be 180. One of them's 30. That means the other has to be 60. You got a 60, 39 triangle. Right? So now what can you tell me that angle is? 30. Now, this sometimes is the toughest part for people. The vector is the hypotenuse of this triangle. Right? So that means with everything tilted, here is one component and there's the other. So I have a triangle now that looks like that. Does everyone see it? Where here, what's going down the ramp, this part is my y component, and that part is my x component. Everyone following me? Yeah. Okay? So I have a right triangle, but down the ramp is the opposite. The end to the ramp is the adjacent. All right, we'll pick back up here tomorrow. See y'all later. Please do not forget this. We're going to start right on this part.
Or next out, the next out, yeah.